Welcome to what is hopefully day one of only a 4-day set of classes. What I have behind me are a set of the index laws that my class, you guys, have been able to come up with through some prompting. And I think most of them are covered there. In fact, I think all of them are covered there by now. So we've got a to the 0 is 1, so anything to the power of 0 is just 1, flat out. All right, there are no way to get powers that equal a negative number or powers that equal 0. Even 0 to the 0 is 1. So if I have two indices or two exponentials that have the same base and I'm multiplying them together, I add the powers. If I am dividing them, I'm subtracting the powers. If I have an exponential to a negative power, that is the same as 1 divided by the exponential, but with a positive power instead. So if I was doing 6 to the negative 2, well, that would be 1 on 6 to the 2. So instead of being 36, it would be 1 on 36. If I have an exponential, and I put it in brackets, and I raise that to another exponential, then I multiply the powers together. If I have a fractional indice, and this is going to come important in a moment, if I have a fractional indice, then I am taking that root, the denominator of the fraction, I'm taking that root of my base number. Then the last two are pretty much the same, that if I'm raising multiple things inside a bracket to a power, everything gets raised to that power. So if it's a times b, all to the power of m, then it's a to the m, b to the m. If it's a divided by b, it's a to the m divided by b to the m. So the other interesting thing about this is that some of them are technically not complete. What I would like to do is get you to consider this one. So I'd like you to consider that one for me. If I was going to write that as a root of something, how would I write it?
3 root a to the power of 2.
3 root a to the power of 2. There is a disembodied voice coming in and doing that for me. Thank you. So, what we can do is we can break this into its component parts. Because just as a to the 2/3 can also mean, so yes, you are correct, that it is the third root of a squared. So that is correct. If I split this up, what am I actually doing? Well, I'm doing a to the 1/3 squared, or I'm doing a squared to the power of a third. Both the same, however, this one down the bottom here is the one that is more applicable to what we're doing up the top there. So, a challenge for you is to simplify some of these really complicated ones. So if I had something like this, what does it become? All right. Before you do anything involving square roots and anything like that, or roots, the root symbol, you need to get them to add together. Or you need to get them into one unit. So how are we going to do that? If I have two exponentials and I'm multiplying them together, they have the same base, I add the powers. So let's think all the way back to the younger times. How do we add those powers together? Alright, so what I need is a 2 over 3 plus 5 over 4. So how do I add those powers together? They're fractions, so how do I add fractions together? Yeah, so how do I add fractions together? It's not a trick question. How do you actually add fractions together? What do I have to do so that I can... Yep, thank you, Jenny. I make the denominator the same. So, what denominator am I going to be going for? 12. All right, cool. So, what do I have? How do I turn? I need to turn all of these into 12s. So I have a to the... something over 12 and the something over 12. What are my numerators, please? Eight and 15. 8 and 15. So 1 on the left, times it by 4, top and bottom. And then times it top and bottom by 3. So that's 15. So what do I end up with? Yep. A to the 23 over 12. Now, how do I express that using the root notation that we've been doing? Yeah. So it is the 12th root of a to the power of 23. So we've now taken everything else and we have smushed it into one. Now, I don't know why you'd ever want to do something that bloody big, but who knows? When you're working with really, really big numbers, what happens is that you start referring to things as terms of exponents. All right, so if you guys think to chemistry, there's a big number that involves a 23. Yep, so Avogadro's, that's like, it's at 6.02 times 10 to the 23. This is why it's useful. This is why being able to work with really large numbers is useful, because if I had, so that's a mole of something. What if I had a mole of moles? If I had a mole of moles, how many atoms would I have? So, in chemistry, if I have a mole, M-O-L-E, of something, if I have a mole of something, I have this many atoms. I have this many atoms of something. So if I had a mole of moles, I would have 10 to the 23 times 10 to the 23. How do I resolve an exponential like that? (6.02 squared times 10 to the 46). Yep. Can someone actually give me 6.02 squared? Yep. So it's 36.24 times 10 to the 46. Or I could decide to write it as 3.624 times 10 to the 47 by moving the decimal point over. Cool.